Greetings everybody, and welcome to the first video in the ring section of this algebra series, and today we're going to be taking a look at the definition of a ring as well as some examples. So let's start off with the definition of a ring. Now, depending on which source you take a look at, the definition of a ring might change slightly. So what I'm going to do is I'm going to give a slightly general definition of a ring, but there's a particular definition of a ring that we're going to be using throughout the entire course. So the definition of a ring is a triple R with these two symbols over here, where R is a set. So what's a set? You can just think about that as a collection of elements. Doesn't have to be numbers or anything, just think about this as a collection of just some abstract elements. And these guys over here, well, these look like your addition and multiplication operations. Well, that's exactly what we call them, but at the moment, these are just binary operations. So what exactly is a binary operation? Well, for example, this plus symbol over here, it's a map that takes two elements of your set R and gives you back another element of your set R. So it takes some tuple in the Cartesian product and maps it to. Now, if you want to think about this plus symbol over here as a function on the Cartesian product, or you can write it as plus AB, but that's a little bit cumbersome to write. So usually we put the symbol in between the two elements that we're performing the operation on. So this way we read this as A plus B. So remember, we're working with just abstract elements over here. A plus B doesn't necessarily refer to the addition you usually think with your real numbers or your integers or whatsoever. All we're doing at the moment is we're defining some abstract binary operation on this abstract set R that we're going to be calling addition later on. Well, we might as well call it addition now, why not? And you can write out something similar for this multiplication map over here, but I won't do that because it's basically the same thing. Now, a set with just two random binary operations that we randomly choose isn't too interesting. So we're going to make this a triple over here, satisfy some nice axioms. And the axioms I'm going to list down are actually going to reflect how we usually think about addition and multiplication on the integers. So we're just abstracting the set as well as the operations. A nice way to memorize these axioms, I learned this from Friedrich Scholar if you've watched his lectures on YouTube, is to memorize a Carney, and then I'll just write down another Carney. Actually, you only need this A here, but I'll just write down all of them because it's nice to see. And then finally, we have this D. So we have some axioms involving addition, some axioms involving multiplication, as well as an axiom linking the two together. So this first axiom here stands for commutative for the addition operation, which says, for all elements A, B in your set R, we have A plus B equals B plus A, so it doesn't matter which way you add the two elements together. This next A here stands for associative for the addition. So for all A, B, and C in your set R, it holds that if you have A plus B, you add these two guys together first, and then you add on the C. This is the same thing as taking B plus C first, and then adding your A in after. This N here stands for the neutral elements for addition, which says that there exist some elements which I'll just give the symbol 0 to it in your set R, such that for every single element A in your set R, taking the element which I give the symbol 0 to and adding it to your element A of your choosing returns you with the exact same element. So there's an element in your set R which basically does nothing when you add it to another element. And this is usually referred to as the additive identity. This I here stands for inverse, which says for every element in your set R, there's going to exist an element which I'll give the symbol A, but I put this negative symbol out the front. This guy is also in your set R, such that if you take A and you add it with this other element here, which looks like the same thing, except it has this negative symbol at the front, this gives you back the additive identity, which is 0. And this guy, you usually refer to it as the additive inverse. So whenever you have some element A in your set R and you stick this negative symbol at the front, well, this is referring to a completely different element. It's actually referring to the additive inverse. And if you've studied a little bit of group theory before, you realize that these four axioms here actually make the set R with this addition operation here an abelian group. Okay, so those are all the axioms for the addition operation. Let's take a look at the multiplication axioms. So this is where things might change up a little bit depending on which source you take a look at, as I said at the very beginning. And the one that always survives is this associative property here. So what does associative say? Well, similarly to above, we have for all elements A, B, C, it holds that if you have A times B, note that if you put two elements next to each other, you assume that there's a multiplication operation happening between them. So you take this product and you multiply it by another element of C. So again, this is one element in R, this is another element in R, There's no explicit operation between them, so you assume multiplication. Well, this is going to be the same as if you just take the final two elements first, and then you put an A out over here. So for some definitions of rings, that's basically the only operation for multiplication. Well, every single definition needs some kind of distributive law. As for just pure multiplication, it stops there. So all rings better be associative. Now for this series, we want our rings to be slightly nicer than this. First of all, we kind of want this commutative axiom over here. So for this series, we'll assume that all rings are commutative. Otherwise, we'll have to worry about things like left multiplication, right multiplication, and then that just becomes a whole mess later on, having to split things up into different cases. So we'll assume our ring is commutative, and that just means it doesn't matter which way you multiply two elements together. And we'll also assume that our rings have a neutral elements for multiplication as well. That means there exists some elements which I'll give the symbol 1 to in the ring, such that for every element A in your ring, taking this element which I call 1 and multiplying with any element A gives you back the exact same elements. And you might have guessed what the name for this guy would be. That's called the multiplicative identity. One of the reasons why you might want to have this axiom here is just to avoid some degenerate cases when it comes to ring homomorphisms. For example, if you've studied group theory before, you'll know that if you have a homomorphism phi, and you act on the identity in one group, well, this should give you the identity in your target group. So it's nice if we can have this multiplicative identity just so we can refer to it and enforce it in one of our definitions, just to avoid some funny cases later. And as for this I here, we'll completely avoid that because we've already gotten these three axioms for multiplication. As soon as you pop this one in, then your ring is going to become a field. And that's something we're going to be studying, well, later on in this course, hopefully. And finally, we have the distributive laws, which link addition and multiplication together. And this says for all elements A, B, C in your set R, it holds that if you have an element A, you multiply it into B plus C, then you can distribute that A into those parentheses as you normally would, and you'll have AB plus AC. Sometimes you might also have A plus B times C is equal to AC plus BC. But this guy over here, it's not required for us because we already have the commutative property for multiplication included as an axiom. But if your ring is not assumed to be commutative, then you'll always have two distributive axioms. Okay, and that's the definition of a ring, and just some remarks. First of all, we say that our rings are commutative with identity. And when you say this, it's obviously referring to the multiplication axioms because addition is always commutative and it always has an identity. It's just the multiplication axiom, sometimes you might change it up a little bit. So for the remainder of this course, this is going to be the definition of a ring we're going to take. And one more remark, we usually write, instead of having to write the triple R plus and multiplication, we usually refer to a ring by the name of its underlying set, so in this case it would be R, instead of having to write out R plus and multiplication, when the two operations are clear from the context. So for example, if your ring is the integers, then obviously you'd take the usual addition on integers unless you try to define some other funny addition operation on your ring. And also, because addition and multiplication are both commutative and associative, we can use summation and products notation, and it won't be ambiguous. Usually I prefer not to write this unless I absolutely have to, or maybe that's just because how I've been taught in the course. Usually we write expressions like A1 plus A2 plus dot 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 plus AN just to make things absolutely clear. But I thought I'd remark that because it is notation that you can absolutely use, assume that your ring is a commutative ring. So let's take a look at some examples. If you take the set of matrices of size n by n over something, doesn't really matter, let's say the complex numbers for now, with the usual matrix addition and multiplication, this guy is not a ring. Well, for us at least, because in other definitions of rings, matrices are definitely a ring, but it's not for us because obviously it's not going to be a commutative ring. Some more familiar sets you're used to, for example, Z is definitely a ring. You can check the axioms if you really want to. The rational numbers are also a ring. The real numbers are also a ring, and the complex numbers are also a ring. In all these rings, the additive identity is 0, which exists in there, and the multiplicative identity is a 1. Addition and multiplication are always commutative and associative, and addition has inverses. Multiplication doesn't necessarily have inverses. And these final three sets, Q, R, and C, these guys are also fields because you can take multiplicative inverses of non-zero elements. And you might be thinking, well, is n a set? The natural numbers? Unfortunately, n is not a ring, because just take a look at the addition axioms. There's no additive inverses. So this guy over here does not hold. Okay, so let's think about the integers once again. How about the sets 2z? So these are the even integers. Well, addition is clearly commutative, associative, there's a neutral element, which is 0, and inverses exist as well. And how about the multiplication? The question is there a multiplicative identity? Unfortunately, there is none. So the axiom for the neutral elements fails. Let's take a look at some more interesting examples. Consider the ring Z, but what I'm going to do is I'm going to put square brackets here and then the imaginary unit I. So this I here, this is an element of the complex numbers. So notice we have our ring here, and notice that Z lies inside of another ring C. So in fact, this is a subring. We'll introduce subrings later in the course. And what I'm doing is I'm taking an element, which is I in this case, which is not already present in this ring Z, and I'm going to try to add it to this ring Z. And the way you define such an object is you take the set of all elements of the form A plus BI, where A and B, these guys are integers. And you can check that this is in fact a ring. I'll also note here as well that the addition and the multiplication, because this guy is a subset of C, the addition and multiplication is inherited from C. Which means whenever you have I times I, well, that's just equal to -1, because that's how multiplication works in complex numbers. So yeah, you can check this guy is closed under addition and multiplication, and the additive and multiplicative identities are as you would expect it, 0 and 1 respectively. So this is what we call the Gaussian integers. Now let's do something a little, I guess, similar, but instead of adjoining this element I, I'm going to adjoin the element cube root of 2. So I'm going to do it in the following way. I'm going to take A plus B, but instead of I, I'm going to put a cube root of 2 there. The question is this guy still a ring? The form looks the same as the Gaussian integers. I've just replaced I with cube root of 2. Does it still hold it's a ring? Well, if you check the addition, the multiplication, and the distributive axioms, they all in fact hold. However, this is not a ring because it's not necessarily closed under multiplication. And to see this, just take the cube root of 2, which definitely lives inside of this set, and multiply it by the cube root of 2 once again. This is going to give you the cube root of 4. And the cube root of 4, it doesn't exist in this set in any way. You cannot find it in this set. Okay, so because you can't find it in that set, let's consider another ring. I'll call it a Z, but I'm going to adjoin the cube root of 2 now. And I'm going to define this to be equal to the set A plus a B, cube root of 2, plus C cube root of 4, where A, B, and C are integers. You can check that this guy is in fact a ring. So you need the extra cube root of 4 in order to turn it into a ring. So we'll discuss how to adjoin elements in one of the later videos. Another example, if you've done group theory, you've definitely seen this group before, the integers mod 4. Now with this ring over here, I just want to point out one particular property, namely if we have the element 2 and you multiply it by 2, that gives you 4, but 4, that's the same thing as 0 in this ring, because 0 is congruent to 4, modulo 4. And notice that both of these elements you're multiplying together here, these guys are not equal to 0. So in rings, you might have the situation where you have two things that are multiplying together that are both non-zero, but you still get the additive identity back. This doesn't happen in fields, but it's something that can happen in rings. And these guys, if you want a definition, those are called zero divisors. So sometimes in rings, the usual properties that we're used to seeing in algebra, high school algebra at least, don't necessarily hold. And we'll do one more example to finish off. That's the ring of functions from the real numbers to the real numbers. So this is just the set of functions from R to R. There's no conditions on these functions required. There's no continuity or differentiability conditions, just any map from R to R. This guy is a ring. I believe you can replace R with any other ring as well, but I just choose the real numbers here because we're used to seeing those nice graphs from R to R. You can check the addition axioms, they definitely hold. The additive identity is the 0 function, where 0 of x is equal to 0 for all elements x. And the multiplicative identity is just the 1 function, where 1 of x is equal to, well, just 1 for all elements x. And multiplication is clearly commutative and associative as well. You don't necessarily have inverses, so this doesn't make f from R to R a field, because sometimes you might divide by 0, and that's no good. So this set here is at best a ring. So that's pretty much all for this video on the definition of rings as well as some examples. So next time we're going to be taking a look at some ring properties that you can prove from these axioms. So some of the algebra properties that you're used to seeing in primary school and high school definitely carry over to rings. Some of them don't though, like this property in Z mod 4Z with the 0 divisors that I showed. But yeah, that's all for today. Hope you guys enjoyed, and I'll see everyone in the next one.